What if we could find the antiderivative of this? What would we do with it? What if we do the antiderivative here, Adam? It would end up being a constant because why? What would you do with it once you found the antiderivative of this here, which we don't know what it is, but after doing what? You'd be subtracting, but after, right? Right. So you'd be plugging in pi over 2, plugging in 0, and then subtracting. So this whole thing, this is just like the warm-up of the activity the other day here. This whole thing is going to be a constant, so the derivative of it with respect to x is
0.
Trick question. But Michael, your time to shine is coming up. Rachel, question? Okay. No comment at this time. I'm going to do an intermediate one here, where now our area is varying rather than it's static, like it was here. We did this last week. Oh, the fundamental theorem, this is now a variable here.
Is this the one from the quiz? Because that one was x to the third.
This is not on the quiz.
Okay.
This is not on the quiz. This is part C1/2. Yeah. Why? Yeah, this is part 1 of the fundamental theorem of calculus, which basically says here that you take the antiderivative here. Well, that's why we call it the antiderivative here. This integral will be an antiderivative of this, so when you take the derivative of it, you should end up with the same thing. And that will be the x there that's varying. Why is it minus the derivative when it's plugged in 0 here is because the derivative, one reason is derivative of a constant is 0 again. So that's like both of these were constant in this case. Now part D. What's different now?
Here you have the x cubed as well.
So how's that going to change things? Do we know how to take the derivative of it with just x?
Yeah.
So this is going to be, what's the derivative of an integral going to be?
Just what it is.
And just what we did here, except now it's not with x in it, it's going to be with
x cubed.
Are we done? Not quite. Derivative of x cubed there, which is 3x squared. So if you recall, we did this earlier, the activity last week, similar problem there, that this was really, this part here was f of x cubed, and you're taking the derivative of it. So its derivative is going to be big F prime of x cubed, which is just the function itself with x cubed plugged in. But then remember, you had to multiply by the derivative of what's inside, which is 3x squared. Any questions on that? Okay. The rest of the problem involved this graph thing, okay, where they gave us no formula for it whatsoever. Riley, question?
No, sorry, my shoulder popped.
Okay, I know.
I'm on top of this.
Okay. Okay. So you still need someone to hold the paper for you then. Okay, there you go. Question on all this before I erase it? Okay. So we're asked various questions here. about this graph of little f? And we put it f of t here. And just a reasonable facsimile. This goes up at 2, got 1 here at 0. 3, this went to 6. So from 2 to 4. Up to here to 2, this is negative 2. And then it stayed constant the rest of its life. There's your function. And we're given here a of x is 0 to x, very similar to part the one we did a few minutes ago, except now we're looking at it geometrically. So what is this big A of x here geometrically? What does it do?
Find the area under.
Finds the area between the curve and the x-axis from what to what?
Over like from 0 to 6.
Yeah. Anywhere you want to stop here from 0 to 6. All right. You just plug in your favorite x value. It's going to sweep out this area here. Before we get too caught up with this here, from what we just did a second ago, is there a relationship between big A and little f? They didn't really call big A just because it's an area function, which it is, but they also could have called this big A because big A is a what? It's a what? Careful.
Antiderivative.
It's an antiderivative of f of t, which begins with a, by the way. Therefore, if I take the derivative of this integral, what am I going to end up with? Same thing we did before, except we just don't have sine of the fifth of t.
F of t.
Just plain old f of t. What if you wanted a double prom of x?
F prime of t.
F prime of t. Those are good things to know. All right, so you kind of have an algebraic way of looking at it, but you also know that the function itself is an area function. Karsten.
Is an accumulation function always from 0?
It also could be called an accumulation function as well. It depends on what book you're reading. The ones I like to read, though, begin at 0 here. The reasons why I like it to begin at 0 is when if it's a class there that doesn't have a Jim Fowler video with it, okay, what I like to do is talk. He didn't do it, I don't think, with a 0 there. But what I like to do is I want to consider my function, say, between A and B. A and B are not 0, for example. This could be over here too, but that would complicate things a little bit. But when I make my A of x equal to 0 to x, I should say of f of t dt, we'll get a little bit more of why I made that distinction here, is because what's the area that I want here? Is really, if you think about it, this is the area from 0 to wherever I want to stop. What I want in the end there is big A of B minus big A of A. Area from 0 to B, knock out the area from 0 to A is going to leave me with the area I like. So when I do this argument here, I always like to make it from 0 here, so we can see this come out in living color. Okay. It's not necessary to do it that way, but it's nice. So, what questions did it ask you about this crazy